We are going to talk about stall speeds today. Now, stall speeds is something that I've been asked to do for years, and I never had time, and I never had a good way of explaining it. But over growing up in this industry, I have a simple way, much like I usually do for you all, that we're just going to handle today. Stall speeds are probably the most neglected or misunderstood thing in the entire car world, next to transmissions. Transmission, you can sort of figure it out. Every piece has its function, and stall speed's no really different. The only thing that makes a stall different, as most of you like to refer it to, a stall, which it's kind of annoying, but it is what it is. This is a hunk of metal with fins that has no computer input or anything. It is a pure mechanical piece and has always been that way. The proper stall speed, and why this video is going to be so important, is you have to actually do some math and know your car if you want the best scenario possible. A good stall speed is going to make your 3,000 horsepower engine, if you actually have something like that, make it its best. Or you could have a $500 junkyard build that's beating a 1,000 horsepower engine. It's all about the stall speed, because in reality, the transmission, what I do every day, it does what it does. Our only goal is to make it not slip and hold your power. And the tranny just does what it does. A stall speed has so many different functions in its little metal shell without any input from the driver or a computer whatsoever. And that's what makes this really cool. As an added bonus, I'm also going to be talking a lot about camshafts today, if you didn't know much about those either, because those two go hand in hand like a beer and a smoke. Camshafts with this piece of equipment are everything, and you can tell a lot by what you need in a stall speed and a converter based on the cam you pick out and a couple other things in your setup. So there's going to be some math. Grab a notepad, crack a beer, have a seat, and let's get this done. Some of the things I'm going to be talking about, and most of this is blatantly plain English, and that's why I love it. Car guys that figured this out a long time ago never wanted this to be confusing. Now everybody's confused because we either don't care to know, just want to go fast, or we think everything's a bolt-on nowadays. Excuse me. Everything's a bolt-on nowadays, and you can just slap it in and go without tuning or figuring anything out. That's false, and that's never going to get you your optimal setup in your vehicle. So, I got some spinny things behind me. I got a couple go-go shafts, and I got a magic stick over here. This is your camshaft, as most of you know what that looks like. Everybody's focused on their cam, turbos, engine. We all know about that stuff. But do you really? Do you know what this thing does and how important it is? Okay, that's what we're going to talk about today. A lot of customers, when I talk to them on the phone, you have no idea how much the stuff in your engine affects your drivetrain in a lot of ways. And a lot of you find it hard to believe, and when you do, you're like, wow, that's crazy. So we are going to talk a little bit about cams, the parts that affect your stall speed, the math that it takes to give you the general guesstimate. And I say that not lightly. All this math we're going to do is still a guesstimate, because there is no real formula to get you the right stall speed the first time, unless you are really experienced like myself and many others. Getting an appropriate stall speed the first time for your vehicle is purely about experience. Some of the things that you will have to take into account we'll get on later in the video, but overall it takes knowing your entire vehicle, because your tires, your rear end, your cam, the weight itself, those are just some of the things that all affect your stall speed. Because it's a mechanical piece, it doesn't know what to do. Math is required. Now, let's jump on in, and bear with me. I'm operating a computer. I'm not good at it. There's going to be pauses. I build transmissions. I don't do technology. Now, this is essentially what a cam is doing, diagram of a cam and how it works. Okay, so follow along with me. Some of the things that we're going to talk about, and most of the car stuff in the car world is plain English. The definition is right in the name, as I like to really hammer down on. So one of the most important things is the duration, okay? The camshaft's duration determines how long the intake and exhaust valves are open for. And it's probably the key factor in the amount of power an engine produces. And a longer duration can increase power at high engine RPM speeds, but this can come with a trade-off with less torque being produced at low RPM. We know in cars there's often a trade-off, and it just is what it is. You have to know your vehicle and compensate. The next thing I want to talk about is lift. So a camshaft lift, right in the name, determines the distance between the valve and the valve seat, or how far open the valves are. And the further the valve rises from the seat, the more airflow that gets there, and that increases your power. Plain English, okay? The reason I'm going over this, you guys need to know these definitions because I want to know what these numbers are, and so does your converter manufacturer. Plus, you should know this stuff to help build your car anyway, because again, there's always trade-offs. Now let's go into one of the other things, probably the more complicated one, with more or less affecting vacuum and stuff like that. Lobe separation angle. Okay, the LSA, as it's otherwise known, is the angle between the center line of the intake lobes and the center line of the exhaust lobes. Okay, you can see that center line right through the cam on that diagram. The higher the LSA, that reduces overlap, which improves your idle quality and intake vacuum. But using a wider LSA to compensate for excessive duration, there's a trade-off, can reduce your power and torque output. So in general, the optimal LSA for any engine is related to the ratio of the cylinder volume to the intake valve area. And you need to keep this in mind, especially when you're more or less picking out a transmission that relies on vacuum for pressure. Your chop cam that you all love and you don't care what it does, you just want the chop. Stop doing that. Chop's cool, but if you have a chop, chances are you're gonna need to run a vacuum pump, which the vacuum will control the pressure in like an old Turbo 400 or something, based on the vacuum that pump is helping with through a vacuum modulator on the tranny. So that is insanely important. Keep that in mind. And again, there's always a trade-off. That's about all I need to know, or a converter manufacturer needs to know with a camshaft. The other thing, you guys, and this is from me to you, please stop, and I know other company feels this way, please stop using the word mild cam when you call us and try to spec out your stall speed. That is the stupidest word I've ever heard. No one knows what that means. Most people don't even know what that means, and everybody has their own definition of what mild or aggressive is. Manufacturers that are really trying to help you and do their job with real facts are not going to be able to get you anywhere with the word mild or aggressive. Save that for your buddies when you're drinking beer. Give people like me real facts, real numbers. Have the discipline to learn about your car. Pretty please. Thank you. Now, excuse me while I navigate here. The next thing that we're going to talk about is the general torque converter operation. You guys should know a little bit about this. Not so important as the cam spec. The cam is something you absolutely need to know when configuring your stall speed. This is just kind of how this thing works and what's going on. I wanted to show you it. So, very simplified. The torque converter has three major components, as you can see here. I know there's 5, I can count, but the other 2 over to my right are the lockup clutch and the backing, which really aren't important in a stall speed instance. The pieces that you want to pay attention to are the 3 left pieces, and those are the impeller, the turbine, and the stator. So how this thing works, this black magic piece of equipment that has no computer controls or anything, the crankshaft is connected to the case of the converter through the flex plate, and the impeller is mounted to the case. Okay, those are the other fins. When the crank turns, the case and impeller, it rotates and generates the fluid flow. And the fluid flow is directed against the turbine, which is coupled to the input shaft of the transmission, and that force of the fluid causes that turbine to rotate. The fluid flows from the turbine to the stator, which is that thing in the middle of the converter, that very small silver piece there with the bearing on it. And that freely rotates in one direction due to a one-way clutch. Some converters are spragless, most have sprags, especially OEM ones. It's just kind of the function and build of the converter. There are variances, but overall this is the general idea. So the stator in the middle between the impeller and the turbine basically play the direct role in directing the fluid so that it efficiently interacts with each impeller or turbine fin and can direct the fluid flow. So talking about that stator, and this is just a 60 diagram I threw up. I wanted you guys to see how kind of stuff I do every day. It's just useless, cool diagram. This is a 4L80. This is very simplified of how the fluid is flowing. So, and one thing you guys need to keep in mind when you're diagnosing failures, heat comes from the converter. It doesn't really come from the transmission. The converter is always going to run way hotter, like a good 50 degrees than your tranny. And the other thing is pressure doesn't really come from the converter, it comes from the pump, and converter pressure is a byproduct of what's happening. And going back to that stator, this is kind of what we're talking about. So the stator is your directional mitigator that controls your fluid flow in the converter, and that yellow piece is that one-way sprag, okay? It freewheels and locks, and that keeps your car from stalling out, and when the fluid flow changes and you start going forward, it'll do its job and direct the fluid where it absolutely needs to go, and it's a pretty clear diagram. So a characteristic of the torque converter, and since I'm on this picture, is the stator is probably the most important piece in the thing. A characteristic of this whole black magic piece is it multiplies torque. That's what makes torque converters cool. That's why dragsters go fast and all that stuff. The factor of torque multiplication in these things can be as much as 2 to 2.5 times or more, depending on the design of the converter overall. And maximum torque multiplication occurs at your rest as you start moving. So as speed increases, torque multiplication decreases, and once the impeller and turbine speeds kind of equate, torque multiplication kind of gets to basically 0. And a non-lockup torque converter has about 2 to 7% total engine slippage loss that exists between the impeller and the turbine. And a lockup torque converter, the reason why it's cool is because it allows near 100% efficiency at high speeds because of a single or triple disc lockup clutch, maybe even more. The converter is locked specifically together, and it is extremely efficient, especially for speed, fuel mileage. It might even drop your ETs if it's locked up at certain points on the drag strip. So overall, it's pretty much very simple. You don't need to know a whole lot about what's going on in there, but it helps you to understand. The last thing I want to talk about in the torque converter design is a trans brake. So when a trans brake's used, the converter has to absorb the full power of the engine with the turbine locked. This generates a shitload of heat and pressure, okay? So you need a good cooler if you're using a high stall speed converter, especially, or even a brake. If you hold the brake for like more than 5 seconds, each second is like 20 degrees of heat. And that's where I say back a couple seconds ago where heat comes from your converter. You are coupling your drivetrain to your powertrain with hydraulic fluid, and everything causes friction, okay? Now, the next thing, and there's a quite simply, this is the fluid flow, okay? This is what the stator does. It directs it in here, and it goes out and down, just like that, more or less. It kind of zigzags. That's another picture of sort of what's going on. And that's a picture I just decided to throw in there because it's kind of cool. So now we talk about the K factor. The K factor is a pretty simple equation that just needs flip-flopped. This is for guys that don't necessarily have a dyno graph that are figuring out a brand new setup. I will be going over a much easier way with the dyno graph, okay? So stall refers to the maximum speed that a motor can achieve against the converter when the turbine's locked. And that essentially correlates and is the K factor. So before we get into that, the higher the stall, the less efficient a converter is. Why would you want something like that? Higher stall speeds are for the drag strip. They allow the engine to get into the meat of the power band much, much quicker, okay, when top end more so matters. On the street, you would want something a little bit lower. This comes into play where I have said over and over, it all depends what you're doing. You can't have the best of both worlds. We can sort of meet you in the middle, but you're not going to be optimized for both. So for the guys that read on the internet that think a 4,000 stall just because the number's higher is what they need for their car when it doesn't even call for it, just stop. You're going to have a bad time and nobody likes it. For the guys that want the best of both worlds, you're gonna have to compromise. You just are. There is no best of both worlds. You can't tow, you can't race, you can't off-road and all have the best optimal setup for what you're doing. It doesn't exist. My advice, and along with many other experienced guys, when you're building a car, you pick a specific thing that that car is doing and you will have an optimal setup for it. There is a lot of street strip guys, and this is where it's sort of okay. You're raising hell on the street and raising hell on the track. Let's say your engine actually needs a 4,000 stall converter, but you're a street strip guy. So you're gonna actually decrease your stall speed if you actually need 4,000 because you're not gonna be doing 150 or 176 on the street from red light to red light in your podunk town somewhere in the middle of nowhere. You want to get that quarter mile red light to red light race, which probably isn't even a quarter mile, it's probably an eighth mile. In that case, to get you sort of the best of both worlds, you're going to take that 4,000 and sort of decrease it down to like a 3 to 3,600 stall speed. It will have the bottom end to comfortably sort of drive it, and it will have the top end to actually get you a decent race. But you will not have the best of both worlds. You will not be optimized for one or the other, but you're making a compromise to have both. And that's why what I'm saying is important. Either settle and do both and realize you won't be optimized, or be serious about your drag strip and optimize it. Stop driving on the street unless you're a psychopath and don't care if the vehicle, takes a little while to get going because of that high stall. It's going to be really uncomfortable. It's going to have shitty gas mileage, and I know we don't care about anything like that, us car guys. I certainly don't. Well, now gas is expensive. I didn't used to care. On my end, the reason why I hate it is because heat comes from the converter. The higher the stall for what you're not using it for, you're going to build so much excessive heat, it's going to affect the durability of your transmission, okay? That's why I don't like this. So for the guys that think they can do it all, please stop, pick something, and stick with it. That's the best rule of life. Now, I'm going to be doing a little bit of math on screen here, mostly just throwing shit up, but I'm going to pull some numbers right out of my ass. We're going to figure this out, and I'm going to give you a sample equation, okay, of a K factor algebraic equation. What we're going to do, if a motor has 400 foot-pounds, 500 foot-pounds, 400 foot-pounds of torque, we'll go with 400. 400 foot-pounds of torque, and stalls a particular converter 3,000 RPM. So we're going to put K equals 3,000 divided by the square root, and I abbreviate that all the time by SQRT, which is the actual equation, SQRT of 400 foot-pounds. The square root of 400 is 20, okay? When you figure that out, it's going to equal 150. Now hold on to that 150 because we're going to turn this equation around, and instead of dividing, we're going to multiply it. So since we now know our original K is 150, we can predict a new stall speed a little bit. Let's say torque is increased a little to say 500 foot-pounds. So now we take our original 150, we've added a little bit of power, we're now at 500 foot-pounds. The new equation is going to be RPM, which is your stall speed. So RPM equals 150 times the square root of 500. And that will equal 3350, which is, most companies don't do a 50 increment RPM stall speed number. They usually do like 200 RPM increments. So our new stall speed, roughly, before we factor all this other stuff in, is probably going to be either 3200 to 3400 stall, which is an actual converter you can buy. This formula isn't perfect, but it's a damn good guideline. And it's really easy. You guys see it. There it is on screen. Rewatch if you don't understand. If you can do basic math, you can do this. And if you have a little bit of experience, you can predict what your motor's doing if you have a brand new setup. If not, your converter manufacturer will certainly help. I can help you a little bit. I mostly want to stick to transmission things. I'd rather you call a manufacturer that actually builds the things rather than me. But I will help you. I do it all the time. I had to learn how to do this because I get that question every day. All right, so for that being said, your street strip guys, a general guideline for you is, mostly for the street guys, you want to pick a converter kind of in the 2500 to like 3200 stall range. Typically, most experience that we've had, we found most street guys pick like a 2800, 3000 stall. That's where you're going to be happiest on the street, mostly. And that all, again, depends on your setup, but these are all general guidelines to help you. So the K factor is your most important, most exact, but not perfect factor in calculating this stuff. The other thing you guys got to keep in mind is, in the future, when you already have figured this out and you have a stall speed, let's say you want that bigger turbo or that brand new intake or something like that. The turbo is not really a minor change, but an intake is a minor change, even pipe size. Those minor changes will affect your stall speed ever so slightly, just enough, and you need to keep that in mind. So much like the Japanese stuff I deal with, where every little damn thing you got to tune for, which is really annoying, but when you learn how to do it, it's not so bad. Same thing with stall speed, and same thing with your LS motor. You probably will need to tune ever so slightly for it, which for some reason we're all okay with, but we're not okay with tuning the transmission or tuning for the stall speed. I don't know why, but it's something you guys need to stop being lazy about and start doing. That goes with mild changes, and that's all because torque converters basically operate off of centrifugal force, and it has no inputs whatsoever. So it's going to react to what's actually happening in the car, and that comes to flash stall rather than advertised stall. We're going to go back to the basics now. This is more overview of one of the most important things I think you guys should have ready, and I know no one saves it, much like my damn transmission instructions, which you all tend to just throw away because you want to put the thing in and go. Stop doing it. That's wrong. Please read every piece of information on the aftermarket part you are putting in your car. So this is a cam card. This is probably neglected, much like my instructions, because every time I ask for it, when you guys ask me to help you with a stall speed, none of you have it available or even know where it is. You just say, I have a mild cam, and quite frankly, I seriously hate it. I hate it more than you guys realize. And I do my damnedest, and I probably get you close. But I hate doing that too. I hate getting people close. I'd like to get them something they really like. Going back to the basics, each cam comes with a little ID card shown here. Now, this is called a cam card. Once again, please save it. It's a piece of paper. Keep it in your wallet. Keep it in your glove box. You should have some general guideline file for your car so you know what's going on, so you can have the best setup possible. This will have all the cam specs on it, including the two most important things, the lift and the duration. And again, the lift is the distance the valve travels to its maximum open position, and it's the key factor in torque production. Duration's the amount of time that camshaft can hold the valve open. And again, duration at the 50, known as the 50, so 0.050 inch, which you guys see on that card in the little center there. That's the general rule for the cam manufacturer that they use to measure it. It's the more accurate indicator of when the cam is going to begin its power band. Your cam card will include the lobe separation and the center line as well. These two are probably what most people want to know that they never knew about. These two specs will tell you how choppy the cam is, i.e. the fucking chop. And sort of how well it's able to idle. So the chop equals lobe separation and the center line. That's your chop and how well it's able to idle. Lower number means less vacuum and decreased idle quality. The need for higher stall increases as those numbers decrease. So please keep that in mind. You can tell so much from this little piece of paper. Now, some of the other factors in this that you need to start factoring in are use the curb weight of your vehicle, or, you know, in general, the weight as the vehicle sits without you or anything in it. So stop by your nearest truck stop and weigh your car. Don't sit in it, just weigh it. Most people, when they give me a number, they get it confused with gross vehicle weight, which is the weight that the vehicle is plus what it's designed to carry. That is wrong. That's going to throw everything off. Then you're going to get pissed off at me because I was given the wrong information. Please keep in mind, we are only good for the information we're given. That goes for tech support, helping you figure out your stall speed, everything like that, okay? So please be exact. It's not hard to stop by a rest stop. Now, the torque converter's output comes from fluid pressure versus resistance. The heavier the vehicle weighs, the more resistance that there is going to be in moving it. The lighter the vehicle takes less resistance to move. This brings us to resistance against the pressure that's trying to move the vehicle. The more resistance, or like weight, against the torque converter, the higher the stall speed is going to be to move the weight. The less resistance moving the vehicle, the lower the stall speed in the torque converter. And even if your cam says you need a 4,000 stall, you probably don't. So a good example for this thing I'm talking about with weight differences and stall speeds, which correlates all the way back to advertised versus flashed. Advertised is what you see in Summit Racing and what you put in your car and what the cam says. So one time, not too long ago, maybe a year ago, I was helping my buddies up at Independence Ford up the road with a 32 Ford Hot Rod, which is a fiberglass kit car. Well, in this instance, it was a fiberglass kit car. And the guy picked all this shit out that says he needed a 4,000 stall. The car weighs 1,800 pounds. There's literally no resistance. And I don't really know exactly anymore how much it weighed, but it was around 1,800 to 2,200. It was an extremely light car with a turbo 350 transmission that I built for it and a 383 stroker. Guy insisted he needs a 4,000 stall, being the typical car guy that we all know and love. But it wasn't true, because when you factor in his big rear tire and that rake stance and the weight with the rear end ratio, which I completely forget what it was, it actually ended up being down around like a 2,000, 2,200 stall that he really needed to do what he wanted and actually optimize his setup for the street and the cruising that everything he, expected out of the car. If I would have put a 4,000 in there, like he recommended, this thing would have gone nowhere. It would have been a dog and a half. So that's a small example of weight is one of the most important factors after the K factor that you need to factor in. And that just kind of comes from experience and the pure definition of what I just went over. Heavier is going to affect things differently. Lighter is going to affect things differently. It's all pressure versus resistance. Okay. Now we're going to look at a couple more things. I'm just going to the next slide. And before I forget, let's talk about ratios before I get into this. I'm just going to leave this up. The ratio of your rear end is more important than you realize. So this is another huge factor. So as the ratio gets larger, the engine has to turn more RPM to make the axle rotate the same number of revolutions. A 308 to 1 rear gear ratio is kind of like a road gear. And as the engine turns the drive shaft, 308 revolutions for every 1 revolutions of the axle. So a 411 would gain more low end torque. Pretty simple, right? It's also, 411 is a gear ratio popular in drag racing that also compensates for larger tires. Okay, the taller the tire, the more wheel rollout you're going to have, which is another important thing, but not as important as the weight, the cam, and how you're typically using it. And most ring and pinion gears are designed for a 26-inch tire, but a lot of guys anymore don't even run that. They run a 28, a radial, a slick, this and that. There's all kinds of different scenarios that you can, it's like Legos. You can put together any piece in any car and make it your own. Putting it all together, the effect of gear ratio, tire height, and weight is what you want to consider after you factor in your K factor, okay? So in general, let's do some more quick math. Vehicle with a curb weight of 3,500 pounds, not gross, curb, okay? If our test vehicle here has 373 ratio, which is the middle ground and what basically I personally like because it's easy to figure out and it's really the best of both worlds. And you have a 26-inch tire, the gear ratio will run true because of the tire height. So we have 373 to 26-inch tire. That's going to be an actual 373 to 1 gear ratio. Now, if we had changed the 373 to 456, the torque converter would stall less due to the actual lower resistance required to move the vehicle, okay? With the 373 ratio, if we went from a 26-inch tire to a 27.5-inch tire, the rollout of the tire would actually give us a 355 ratio. And we'll go over calculating ratios. I don't feel like getting into it today, but it's not truly that important because most guys in this video are going to be dead set on what rear gear they're going to want to run. But you can all, tires and rear gear ratios go hand in hand, and that all goes hand in hand with stall speed. So with a 373, if we went from a 26-inch to like a 28-inch tire, the rollout would be basically a 355 output according to my math here. And that in essence is one whole gear ratio less, okay? So nitrous, sorry, I didn't mean to call it NOS, I hate that word. Nitrous and superchargers like the longer, lower gears to give them, the time they need to load it up. So the same, if we went from a 24.5 to a 26-inch tire, then your ratio will increase one whole set more to a 390 output gear. So do you see where this is going? And we are going to talk a little bit about the easy way to kind of skip the K factor if you guys actually have a dyno graph. So this isn't exact at all, but it is another really rough, much rougher guideline. So here we have a really piss poor graph of a dyno graph that looks like it was done in Microsoft Paint. But you guys get the general idea. You always got two lines, horsepower and torque. And you can see the green highlighted area is your power band. The general rule for the baseline of a stall before factoring your tire size, rear ratio, and everything else is you add 500 RPM to your minimal power band, which will be, in this case, 2000 is where we start going into the power band. So you're going to start with, I expect to have about a 2600 stall. And then you'll go from there, factor in your tire height, rear ratio, and all that stuff. And that, again, all comes from experience and what I just talked about. So to just really kind of go over that stuff again, if you increase the gear from like a 373, which is common, to a 456, you'll have less of a stall. So factor that into your 2500 because of the lower resistance needed to move the vehicle. And with, you know, your tire height and everything like that, you might change the actual gear ratio based on what you did to the tire. And please don't do it for looks, do it for function. So if we went from a 26 to a 28-inch tire and we were using a 373, the rollout of the tire will be 355, rear gear output. You know, that's one hole less. And if you go from a 24 to a 26, then the ratio will increase to a 390. That's just very simple math. Just step it up a gear based on the inch of your tire. So in general, and here's another piss poor one that's more complicated. You know, they're wildly different torque curves will be harder to read. This is, again, a general guideline for a smooth torque curve. You know, if you got a wild torque curve, this is going to be a little bit more difficult. Let me get back. This is me piss poorly operating my my computer program here and working cameras and thinking and mathing, maths and everything else. So wrapping up, you know, how should you start choosing a torque converter stall speed? You pick a stall that's 500 RPM higher than your minimum peak power band, okay? Don't start at the peak because you're going to be up in like the 6,000 RPM range. Start at your minimum, add 500 if you don't feel like doing the K factor and you have a dyno graph. Typically, a good street stall converter is like around 28, you know, maybe 3,200. That's typically where most guys are happy. A general guideline, let's go back for your cam card here. So on your cam card, you're gonna have your duration is what you're gonna follow. So a general rule, if you don't wanna do the K factor and you don't have a dyno graph, and you just have your cam card as a baseline only, if your cam duration is under 248 degrees, go for like a 2,000, 2,400 stall converter as a baseline. And if your cam duration goes up to 268, do like a 24 to 3,000 stall. That would be better. But again, it's only a baseline. And that's honestly as simple as that. 500 is the golden number. Size of the torque converter, it depends on your vehicle. In the LS world for performance, the most popular is a 9.5-inch billet torque converter, which billet you need. Talking about converter strengths, 500 horsepower and up, you will need a single disc billet at least. I know nobody wants to spend the money, but you're gonna have to or it's gonna fucking grenade. If you got a heavier vehicle, and especially if you're towing or using lockup and you got a decent amount of power, you're gonna want like a 10.5-inch because of the bigger lockup clutch and the rolling resistance factor in the vehicle. It's pretty simple. Most cars that are just street driving or under like 400 horsepower, you can get away with an OEM type aftermarket 12-inch or 11-inch. That can be usually stalled up to 2400 if you don't got a lot of juice, not a big cam or anything like that. The other factors that I would like to talk about is, again, the rear gear ratio. Just wrapping this up, most people know their rear ends, but they don't know how it correlates to everything else. So in heavier cars with like a 273 or like a 308, a low gear value, since you need that extra force because of those gears, which are also harder on the transmission as well, keep that in mind, a torque converter is going to end up stalling higher. You know, on the other hand, a lighter car with a higher gear, like 411, 456 or something like that, you won't need to reach such a high RPM. In short, the trans has very little to do with any of this. My job is to hold your power, and that is about it. The torque converter is much more than what I do. So that's why I specifically ask, if you're unsure, I will help you. But I prefer you talk to somebody who really, really specializes in torque converters based on their specific product. Circle D is different than Yank. FTI is different than Boss Hog or Pro Torque or anything else you might find around the country. They all have specific designs, much like we do. A 4L60 is not just a 4L60 from any other competitor like RPM or your local Joe Schmo or whatever. Ours is different, theirs is different, local Joe Schmo's is different. We all do different things and we all know our product the best. So if you have a specific question for each product, can pick up the phone. Do not hammer Messenger. Do not ask us to call you back because we are not going to. Pick up the phone. Stop messaging. Let's talk. Let's talk real facts and knowledge. In some cases, the last thing I want to talk about is an example I'd like to give. There's some videos on the internet where a lot of people praise this and it's actually stupid as hell. There will be a video of a muscle car of some sort in a gravel driveway that is more or less idle, pushing itself along while it's spinning the tires repeatedly. That is something that is an instance of an incorrect stall. It is not that the vehicle has a shitload of power where it can't keep itself still. It's a guy that didn't do his math, and it's really stupid and non-impressive because when he's actually trying to go fast in a mile-an-hour scenario, he's going to hit about 80 miles an hour and top out. It's not cool. It's not fun. Getting an incorrect stall is more like getting a crackle tune in your JDM car or something. It's just dumb. So please do your math. And the other things you could have with an incorrect stall are idle issues, vacuum issues, and all kinds of stuff. So I hope this makes sense. I hope the math makes sense. And I hope I gave you guys a very clear, clerical video on how to calculate your stall speed. And I hate to disappoint, but at the end of the day, it's going to come from experience. So please don't be afraid to fail. I know not a lot of us have as much money as the other or whatever, but you know what? When you fail, you learn. So don't be afraid to do it twice. Try to do the math, figure your car out, and eventually you will succeed. And that's why most companies offer a free restall. Every single one almost does. So this is Ryan from PerformaBuilt. I hope you enjoyed my piss poor calculations and everything that I have in my head about stall speed. Thank you.